Welcome to lesson 8 of my refresher course. Today we're going to talk about probability. So well done for sticking with it so far. It's a lot of work. So talking about probability then. Probability, there's going to be some formulas again in this section, like there are, for example, in the coordinate geometry part or in other parts of the course. This topic, I always think it's kind of better if you think a little bit more, right? So what I mean is you can kind of like, this is one that you can kind of wing it a bit. Like if you're thinking and you're sort of, you're using your smarts, then you're going to be able to do most of these questions, right? So okay, so let's just start with the most, so this is what we want to do today. So we want to talk about the addition and multiplication rules um, for probabilities. We want to talk about conditional probabilities, and we also want to talk about tree diagrams. We want to talk about what's the difference of PA given B and the probability of B given A. Then we want to talk about Bernoulli trials and binomial formula. And then also, like, we're just going to like try to use some real world settings. So, like, with probability, you're going to be able to there's loads of people who understand probability, or understand a lot about probability without ever having studied it or anything, right? So this is one of those topics where you're going to be able to like just use your intuition a lot, right? Which is good because it means less memorizing kind of formulas and things like this. And what happens also, what happens in the exam is oftentimes the question gets given to you in a slightly awkward way. And if all you know is like formulas, that can catch it out. Okay. So let's just bring it back to the very, very basics. So the first of all, probabilities. Oh, sorry, pen wasn't working there for a second. So probabilities, they have to be between 0 and 1. Okay. Oh yeah, I know why. The pen needs this software to be open to work properly. Okay, so let me try this again. So let's talk about probabilities. They have to go between 0 and 1. Okay. So probability of 0 means that it can't happen, and probability of 1 means that it's a certainty to happen. And then anywhere in between will give you the sort of chance that something can happen. Okay. So the way we're going to work out probabilities, a probability, let's say, of some event, let's say the event is E for event, the probability of the event E is equal to the number of possible ways that we could get that thing. Sorry, the number of favorable ways, which is the number of ways that we sort of that are favorable to us. We'll take an example in the second over the number of possible. Okay. So let's just take an example. What's the probability of getting an ace from a deck of cards, right? So in a deck of cards, there's 4 aces, 4 kings, 4 queens, 4 of everything. And there is 52 cards. So the number of possible cards, if we're just going to take, one card from a deck of cards, the number of possible is 52, right? So we could get any one of 52 cards. But the number of aces in the deck so the number of favorable is 4, right? So that's 4 cards out of 52. So this is the chance that you have, and then you can just divide this, right? And you can say it's 1 in 13. And if you really wanted, you could say this is a fraction. So 1 divided by 13 is equal to 0.0769, so 0.077. 0.77. Okay, so you see this thing always has to be like it can never be if we just look at this and we're just counting the number of cards, this will always have to be a positive number or 0, and this will have to be like a positive number, right? And it'll always be bigger than that one. So that's what makes sense. Like for example, we could say what's the probability of getting a card that's between like a card that's between 6 and 9, or let's say 6 and 10. Well, what's between 6 and 10? 7, 8, 9. How many sevens are there? There's 4. How many eights are there? There's another 4. How many eights are there? There's another 4. So this is like 12. Okay. So the probability of a 7, an 8, or a 9 is equal to 12 out of 52. So you could be playing a game of cards and you could be like, I need a 7 or an 8 or a 9 to win this game, and this is my chance of getting that. So 12 out of 52 will be 3 out of 13. Okay, so that's your chance. And then you can put that into the calculator again and you'll get something like approximately 0.235, something like that. Okay. Okay, so this is how we work out probabilities. What goes into these brackets here, like you can be a little bit ad hoc with that. Like, this doesn't have to be some fancy algebraic statement. It just has to be a statement of the event that you want to see. Okay. So I hope it makes sense to you now that probabilities. So like, if we think about the possible values for probability, so the probability has to be between it's a set that only is stuck between 0 and 1, including 0 and 1. Okay, so there's no possibility of having a probability that's greater than 1 or a probability that's less than 0. Okay, so that happens sometimes. Sometimes students write that down. So if you've gotten that, you've clearly gone wrong somewhere. Okay, so now we've got a bunch of formulas to go through. So we've got the probability of A intersection B is given by this formula here. The probability of A union B is given by the above formula, the probability of A intersection B. Then we have more formulas afterwards, and then we can start working with some formulas. Then we have this conditional probability stuff. So we start to get into these sorts of equations, first of all. And what I do with this when I talk about this topic is basically I just draw some Venn diagrams. Right. So this is what I recommend you do. So let's just draw. This first one is this first one here. First circle is for event A, and the second circle is for event B. Right. So this is A, and this is B. Okay. And let's say if something must be either A or B, like A could be anything and B, it's completely general. But let's say A is like heads and B is tails. Okay, so now, if we do a random coin flip, it's just like a point going into one of these sorts of places. Okay. Now, if it's A and sorry, that's probably a bad example. Let's not use that example because there is no intersection in that case. So if it was heads and tails, then there'd be lots of events where I go into this one and lots of events where I go into this one, but never any event where because a coin cannot be both heads and tails at the same time. So that's just a quick example just to kind of describe why we can use the Venn diagram to talk about probability. So basically what we're saying is, let's say the sub event that happens, we're not saying what it is yet. And it's basically it has to be either in this set or this set or in the middle. And it could be there's just a couple over here, right? But then there's lots and lots and lots and lots, lots and lots and lots of events over here, right? So it's more likely to be B, and then maybe just very unlikely for it to be in the intersection. Right? Okay, so let's say we have and with this example we could also go outside. So we've got 3 options, or let's say if we're going to take, sorry for starting and stopping. Let's say we say this is the universe, right? Okay, so this is we can't go, no point can go outside of there. So we can either go here, we can go here, we can go here into the intersection, or we can go here. And we want to work out the probability of going into any of those places. Okay, so the probability of A intersection B, or sorry, A union B. So the probability that if we drop a point in this box that it doesn't go outside, right? That that it goes inside somewhere in here, in between those two. Okay, well, that's going to be the probability of A, right? So it's going to be the probability of A, then plus the probability of B, so plus that probability. But what you see is that we've actually counted this piece of the intersection when we included A, and we also included when we included B. So that means we've included twice. So we have to subtract one of them. Okay, so the probability of A union B is the probability of A plus the probability of B minus the probability of the intersection. Okay. Now, the next thing that we can say is that, and this is only true if we have independent events. Okay, so what we mean by this is like let's say, for example, we have this is a coin toss. So A is a coin toss, right? And then this one is a roll of a die, right? Okay, and we could say that A is the event that a heads comes up, and B is the event that either a 1, 2, or 3 comes up, right? And the probability of this is like the probability of this one is the probability of A is equal to 0.5. And the probability of B is equal to 0.5, right? But these are also independent events, right? Like, it's not like the dice or the die is looking at the coin to see which side it's gone down on and then choosing like whether or not what its result is going to be. They're just totally separate things. They're independent, and because they're independent, it's much simpler. So on the leaving cert, we're asked to show that things are independent, or we're told that they are independent and to work out the intersection. Okay, so in that case, it's just the probability. So the probability of getting, let's say, for example, we want the probability of A intersection B. So this means the probability of heads and like a 1, 2, or 3, right? So in that event, we have to multiply the probability of heads and multiply that by the probability of the probability of the second thing, right? So it's basically like two consecutive events. So you multiply. Now we're going to see this in a lot more detail in a minute when we go to talk about tree diagrams. But basically, if you have two events that are consecutive, then you multiply them. So this is sort of like I think of it. Imagine if you had two hoops and you're going to throw a ball and you want the ball to go through both hoops. Well, you have to think, what's my chance of getting it through the first one? And then you have to think about what's my chance of getting to the second one. But like, if you haven't gone through the first one, then it doesn't matter if you've gone through the second one. So you only want to look at the times that you're getting through the second one after you've gone through the first one. So that's why you're multiplying. We'll see this in more detail when we look at tree diagrams. So here's an example of a couple of formulas that you can use that just you can make sense of with Venn diagrams, except for the second part, which will make sense of using a tree diagram. Okay, so we have mutually exclusive events. Basically, if there's mutually exclusive events, then basically both events can't happen. So, event A could be the heads on a coin toss, and event B could be the tails on a coin toss. And you can't have in the event of just tossing a single coin, then you can have both heads and tails at the same time. So the intersection then is 0. Okay, and then if you have like independent events, basically the outcome of one doesn't affect the other, like we were just talking. So it's just sort of like they're slightly different things. So mutually exclusive means one or the other, not it can't be both happening. But independent means the effect of one. So an example is like, if we toss a coin and we get a heads on the first throw, the event of getting B on the second throw would be independent of the first. It's not like the coin is counting up how many times that it's given heads and then is deciding what the next one's gonna be. Okay, so yeah, so the coin flip is the example of on one coin flip you can have a case where it's both heads and tails. Okay, so so we have the probability that a student plays soccer is 0.4. And the probability that a student plays basketball is 0.3. And the probability of both is 0.1. And we want to find the probability of soccer and basketball, right? So we're going to call this here the probability of S for soccer, the probability of B for basketball. And then we're going to take this formula here. This is the probability of S plus the probability of B minus the probability of S intersection B, which is going to be 0.4 plus 0.3 minus 0.1, which is 0.7 minus 0.1 is 0.6. Okay. Now they're saying, why not just add? Well, we can see it here if we make Venn diagrams. So I'll just go ahead and make a Venn diagram. So the first circle can be for soccer. Second circle can be for basketball. And then we'll have a box to make the universe. Okay, so it's going to be like soccer and basketball. Okay, and what we could do is we could just go ahead now and write down like 0.4 and 0.3, and we would be wrong. Okay, why? Because we need to put the 0.1 into the intersection first. And now when we talk about this 0.4, we mean a 0.4 for the entirety of this set here. So this has to be a 0.3, and this has to be the 0.2. See, 0.3 and 0.1 will be the probability of soccer, which is then 0.4 and 0.1. And then, so that's in total 0.6. So the probability of not playing either then is 0.4. Okay, so it's when you do some Venn diagrams, it becomes super clear. Okay, so we have, what are we saying here? So the multiplication rule, right? So we're going to say, like, let's say we have, we're tossing a coin. The first toss is A, the second toss is B, and it goes on like this, right? And we're now looking for the probability of two heads. Okay, so that's the probability. Let's say A is heads on first throw, and B is heads on second throw. So it's going to be the probability of A times the probability of B. Now this is here is like 0.5, right? And this is 0.5. So this is 0.5 times 0.5, which is a half of a half, which is a quarter, 0.25. Okay. Now, conditional probability. Let's just see where we're going to with this. Yeah, so let's just talk about conditional probability. It's one of those things where, you have a new symbol and can be kind of confusing, right? So what does P of A stroke B mean? This means, in probability, this means the probability of A given B. Okay, so let's draw some Venn diagrams. This is super easy to understand once you draw a Venn diagram. So I'll just do that now. So, okay, so this is the event A. This is the event B. Okay, and okay, so we have the event A. We have the event A. We have the event B. Okay. So the probability of A given B. Okay, so what are we given? So we're just like, imagine these are two hula hoops laid on the ground. A drop of water comes down and lands somewhere in the two, right? So it could land here, it could land here, it could land here, or it could land outside. Okay, good. Okay, but the probability of A given B. See, we've been given, this is the crucial thing, given B. So we know that it's landed inside of this hula hoop, okay, this drop of water, right? So we know that we're inside of this one here. Now, what's the probability of A given B? Well, basically, it's like, okay, given that that raindrop has landed inside of this hula hoop, what's the probability that it's also landed inside of the other hula hoop? And the only way that that can happen is if it's landed in the intersection. Okay, so if it's landed here, like we know that it's landed in B, right? Because we've been given B. That's what that vertical line means. Okay, so the probability of A given B means that we know it's landed inside B, but what's the probability that it's also landed in A? Okay, so what we need to do is we need to work out how much this piece is a fraction of the whole. Okay, so what we're saying is, let's make a fraction. So let's just work out like what proportion of the set B is inside of the intersection. So that's a probability of A intersection B, which is this piece, divided by the probability of B, which is the whole thing. So in this previous example here, you see, this is like, you see, B is in total like 0. The probability of B is in total like 0.3. But the probability of the intersection is 0.1. So you got this 0.1 and this 0.2. So that means that the probability of A given B, or I should say, sorry, it's soccer given basketball, is the probability of S intersection B over the probability of B, which is 0.1 over 0.3, which is 1/3. I hope that makes sense. So what we're saying is, you see, like 1/3 of the out of all the probability that's in here, right, which tells you how likely you are to be in whichever piece of it. Like it's basically split. 1/3 of it is in this beat, and then 1/3 of the total probability. Right? Okay, so the probability of A given B then is this. Now, the other question that we could ask is, what's the probability of B given A? So this time we know that we know the raindrop is landed in this side here, but it could be completely different. Like for example, with this example here, the probability of basketball given soccer is the probability of the intersection 0.1 over, you see this number is different. So it's actually the probability of soccer is 0.4. So it's actually 1 in 4. Okay. So the probability of A given B, where is it? The probability of A given B is not the same. These are not equal to each other. Okay. Now, something that we can do, though, and then we take a new page to write it down. And this may go a little bit off the course, but it's okay. So the probability of B given A is equal to the probability of A intersection B over the probability of A. And the probability of A given B is the probability of the intersection over the probability of B. And just as it happens, we can just observe that this term is in both. So if I now multiply that up there and this up there, so let's do it. Probability of A times the probability of B less A, then the probability of B times the probability of A given B. I think I might have said less here. So we can set these equal to each other, because if we multiply that probability of A up here, then that's equal to, this is called Bayes' theorem. So this is a big theorem in probability. And essentially what it gives you the ability to do is, see, we have a connection between the conditional probabilities. So, B could be the event that it's cloudy, and then A could be the event that it's rainy. So that's like, the probability of B given A is like, what's the probability that it's cloudy, that it's raining, given that it's raining? And he says probably pretty high. It doesn't really, sometimes you get sun showers, but not often, right? But this one means something different. What's the probability that it's raining, given that it's cloudy? Well, like in Ireland, it's cloudy all the time, but it doesn't rain all the time, right? Sort of thing. Okay. So not this summer, but in general, I suppose. Okay, so let's have a look. So let's have a look at how this works out. So we're going to draw a couple of Venn diagrams. So we have, hope this is okay going through this stuff at the pace I'm going through it. I just sort of, just these little things, like there's not too much to this stuff. It's just, sometimes you can just get a little bit confused about what's going on, but okay, let me, not for really too good a reason. So, like there's some things on the course that are genuinely kind of tricky, but this is something that's a bit more intuitive. So, okay, so in this first one, I'm just going to put in the numbers, right? So there's from 100 students, so there are in total 100 students, right? So 60 play soccer. So I'm gonna have to make this soccer and basketball and make this one soccer and basketball. Okay. So 60 students play soccer, 40 students play basketball, and 20 play both. So this is 20. Now 40 play basketball, so there's another 20 here. And 60 play soccer, so there's another 40 here. And now what I want to do is I want to turn all these into probabilities. So let's work out the probabilities here. So this is 60 out of 100. That's 0.6. This is 40 out of 100, 0.4. And this is 20 out of 100, 0.2. So this is like 0.2. Then this is 0.2. Together they give us our 0.4. And this is our 0.4. And now we want to work out the probability of soccer given basketball and the probability of basketball given soccer. So the probability of soccer given basketball is the probability of the intersection divided by the probability of basketball, which is 0.2 over 0.4, which is half. Now, the probability of playing soccer, that's the probability of playing basketball, given you play soccer, is the probability of the intersection. So that's basketball intersection soccer. Doesn't matter which way you do it. You know, if you do S intersection B is the same as B intersection S, all over the probability of soccer, which is then going to be equal to the probability of B intersection X is like 0.2 over 0.6. So this is equal to a third, right? So what it means is that, like, what does it mean? It means that if you're a soccer player, the probability that you're also playing basketball is higher than if you're a basketball player, right? Like, so basketball maybe is, you know, students only play basketball, they're more likely that they only play basketball as compared to another sport. Okay. And then let's not worry about that. Okay, so let's now talk about the next great way that we have of thinking about probabilities, and that's to use use a tree diagram. Okay, so basically, with if you think about like events that could happen, like walk out your front door, you could go right or left, but then you come to a roundabout and you could go one of three ways, and then this one goes up and there's two ways. And so if you think about how all the probabilities of doing stuff sort of branch, they make these kinds of tree structures, right? And it obviously can get super elaborate. So you'd start off here and you could end up in any number of different places, and who knows where you would end up. Now, like when we're going to draw these tree diagrams, most of the time we're actually going to draw it where it's only two possibilities, okay? To keep it simple, because these things get like there's too many branches very quickly. So what we're going to do is talk about three consecutive coin tosses, okay? So the first one is like it could go either heads or tails. So this dot there is heads and the other one is tails. The next one, it's either heads or tails, or heads or tails. And the next one is either, let me just do it like this. And the next one is either heads or tails, or heads or tails. Huh. Never make these diagrams big enough. Okay. Then heads or tails, or heads or tails. So always the upper branch is going to be heads, and always the lower branch is going to be tails. So let me just label all of those, okay? So, and let me break this now into, you know what? I think I can use a different pen for this. No. Something like this. Sorry if it's a little bit messy. Okay. So the first one then. So we have heads or tails, heads or tails, heads or tails, and then heads or tails, heads or tails, heads or tails, heads or tails. Okay, and onto each of these branches, we're going to put on the probabilities of each one. So this is 0.5 and 0.5. And you know what? They're all 0.5. Almost there. Let me just write, I think it'll be quicker. 0.5, 0.5, 0.5, and 0.5, and 0.5, 0.5. The reason why I'm doing all this out, it is worthwhile. Okay, so what happens is, let me just also move all of this to the side a little bit. Need a bit more space. Okay, so what we have here in the end is 3 heads in a row. Then we have 2 heads and a tails, right? Then we have a heads, a tails, and then a heads. Then a heads followed by 2 tails. Then the same thing, but with just T in front and the same letters repeated afterwards. So THH, THT, TTH, and TTT. Why did that? Yeah, there we go. Okay. And these are all the possible outcomes that can happen. We see that there are 8 of them, but there are 8 possibilities, right? There's 8 possibilities. So each of them are 1 and 8, right? Each of them are 1 and 8. Okay. But what we also see is in order to get heads followed by heads followed by heads, see, we need a head followed by heads followed by heads. And that's where it's sort of like these are independent events, right? The second coin toss never depends on the first coin toss, right? This totally independent, right? That means you could have an infinite number of heads in a row, like, but it's just very, very unlikely to have that. But there's no reason unless the coin is faulty, but if it's a fair coin, so if it's got equal probability of landing on both sides, then it's just going to be this one multiplied by this one multiplied by this one. So 0.5 is the same as a half, right? So that's a half by a half by a half. If we multiply the 3 probabilities, we get an 8. Okay. And that's how we can see that actually when we count up the probability of 3 coin tosses and we divide by so we just look at the number of possibilities, then we can see that it's 1 and 8 when we look, but also when we multiply any of the branches. Now let's say we're going to do one final thing with this, and we're going to look at the possible probability of having exactly 2 heads. Okay, so where does that happen? It happens here, it happens here, and here. So that's 3 out of 8, right? But what it is also is it's this branch, this branch, and this branch. It's those 3 branches. Now, the probability of the first branch is 1 in 8. The probability of the second branch is 1 in 8. And the probability of the third branch is 1 in 8. And then this is 3 different, so we have to add up the 3 different possible ways that we get there, right? So if getting there is just getting 2 heads, then we have 3 different ways that we can go in this tree diagram. Okay, so this gives you a couple of great rules. So if it's we can have and, or we can have or, right? So if we need A and B, we have to multiply the probability of A by the probability of B. So this means going down a particular branch in a sequence. This is this and this and this and this and this. So you're multiplying the whole time, which is how we got to the 1/8. Okay. But or A or B, this means that we add the probabilities of A and probabilities of B. So we add them. Now, A and B, they're always different. So let's say A is the event that we get like 2 heads. So A is the event, let's say, that we get this result, and B is the event that we get this result. And then we have probability of C, like A or B or C, right? So then, do you see what I'm saying? So this is why we have to add. So this is a nice picture that's very, very intuitive that actually kind of carries these rules. If they're independent events, then we can draw a diagram like this. If they're not independent events, it's not on the course, okay? Because it gets, then you have to consider the dependency and you get into a lot of complications, and we're not getting into these kinds of complications like right away. Okay, so now we have a bag has 3 red balls and 2 blue balls, and 1 ball is taken out without replacement, and then draw 2 branches to calculate the probability of red, then blue. Okay, so let's have a look at this now. So we're going to only draw 2 branches, okay? So we'll go from here to here, and then we'll go from here, 2 levels of branching, I mean. So this is like, let's put it like this. This is event number 1, and this is event number 2, okay? So we can either get a red or a blue, and then we can get a red or a blue, or we can get a red or a blue, okay? And the probability of a red, well, you see there's 3 red, and there's 5 in total, right? So the probability of getting a red is 3 out of 5. And the probability of getting a blue is like 2 out of 5, right? So this is like 3/5 here, and this is like 2/5, right? Okay, and then this here, now I'd be tempted to write 3/5 again. So what we want is red, then blue. So what we're after in particular is to work out the probability of going out this to here and then to there. So this is the probability that we want to work out. So we have to work out what the probability of this branch is, and this one, and then the rest of them, okay? So the first thing to note is that without replacement. So in the second case, it's actually a total of 4. And if I've already picked out a red one, now there's actually 1 less red one. So this is 2 out of 4. And this is also 2 out of 4. So the diagrams can be a little bit involved. So now it's like, because we haven't replaced it, okay? So now we have 3. So this is 3/5 multiplied by 2/4, or just like 1/2, okay? Which is 3/10. Okay, and then, so this one here is just comparing A given B and the probability of B given A. And an example they always give is medical tests. So you have like, you have a disease, and someone can have it or not, and then you have a test, okay? So let's say, basically the probability that you test positive given that you have the disease is completely different to the probability that you have the disease given that you test positive, okay? All right, so the probability that you test positive given that you have the disease is like, this is kind of talking about like how accurate the test is, but then if the probability you have the disease given that you have a positive result is talking about the quality of the test, if that makes sense, So they're not the same as each other. Okay, so then, when you have independent events, then the probability of A given B is equal to the probability of A, I think, is it? I don't know. Let's just move on. Okay. So the next thing that I want to talk about now is these Bernoulli trials, okay? And what we're going to do is we're going to end up using this formula here. This is probably not the best notation to use, but so what we're going to do is we're going to have 2 independent events. So we have trials, right? So we have a trial. The first trial could be the flip of a coin, right? Or the throw of a dice or something like that, right? And then we're going to do this trial like many times, okay? Many times in a row, okay? And what we're going to do is we're going to talk about success and failure. We use P and Q for this, right? So it can either be success or failure. So P is the probability of having success. So that was like, what's the probability of getting an odd number when you cast the die? Then there's 3 ways that you can get odd numbers. 3 out of 6, right? The probability that you can get an even number or not that is also 3 out of 6. But then the probability of getting like the number 1 is 1 in 6, so that's my P. And then the probability of not getting a 1 is 5 out of 6. Okay. Okay, so what we're going to do, so let's have a look here for a second. And then we're going to look at the binomial distribution. Okay, so this is kind of, let me just sort of explain this in my own kind of way because it looks a little bit kind of funny. Right. So let's say we have a coin flip, or let's say we're going to cast a die. Let's go to that example. So we're going to cast a die. So this is a die roll. Okay. Okay, so a dice is 2. If you didn't know that, a die is 1. Okay, so what's the probability of getting a 1? That's going to be 1 in 6, right? So let's say we want to work out the probability if we roll 10 times that we get 4 1s. Okay, and we're going to have to get a bunch of quantities for this formula. We need an N, we need a K, we need a P, we need a Q. Okay, so what's N, first of all? Well, N is the number of total times that you throw the dice. What's K? K is equal to 4, right? This is the number of successes or favorable outcomes that you want. This business of capital X is the number of successes, and capital X is equal to K, and all this business, this is just sort of notation stuff. Like, we're not going too much depth into probability, so don't get bogged down like too much with notation. Just understand it in an intuitive type of way. Okay, now what's the probability? P is the probability of success. So success for us would be rolling a 1, and the likelihood of rolling a 1 is just 1 out of 6 because there's only one, and the 6 numbers, so it's just 1 out of 6. Okay, and then the probability of not rolling a 1 is 5 out of 6. Okay, now let's say the following. Let's say I was doing this game, and let's say I got 4. I rolled the die 10 times, and the first 4 shots, I got a 1, and then the rest of the time I didn't get a 1. So then I would have to get a P followed by a P followed by a P followed by a P, a Q followed by a Q, and I'd have to multiply all these out, right? So that's 1/6 to the power of 4 times 5/6 to the power of 6. Let's just do a quick translation back to the formula. This is P to the power of 4, and this is Q to the power of 6, but 6 is 10 minus 4. See? So that's P to the power of K and Q to the power of N minus K. So we already have these two. It's just, this is P is just a number of, P is just a number of, so we have to multiply out P by P by, no one wants to write this, right? So that's why we always have to shorten everything. As soon as we shorten something, then it looks a bit weird. Maybe we don't remember and so on. That's just like, what happens with maths. It just, basically it's like an abbreviation. Like if, you have some long word and then you like CAO, right? Well, I don't even know what it stands for, right? But you know what I'm saying? You can kind of shorten something and then lose the meaning. So that's why this might be confusing. But if you just think about this, it makes total sense. Well, what about that bit? And the reason why we have this bit here is because the question that we've said is just to get, all we want is 4. We want 4 from 10. We want 4 of the 10 results to be a 1. Now, this is more specific than that because this is 4 from 10, but also the first 4, right? Because this also works. 3 P's, then a Q, and then a P, and then on the rest Q's. That also works. And I can move that P along, and then I can start again. And I have all the different ways of rearranging that. So in particular, I want to say what we have is we have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 of these boxes to fill. And we want to figure out the number of ways that we can put 4 P's into these boxes, right? Right. So we have to count up because what we have to do is we would have to then just add them all up. This is going back to our tree diagram, you see. So this would be like, you remember we were talking about how can we get like this question, like how could we get two heads? What's the probability of getting two heads? Okay. Well, we can either go this way, out this branch, we can go this way, or we could go that way, right? And then what we did was we just worked out the probability of each of them and then added them all up. But it turns out that once you know that number and once the probability is always the same, right? So it's not a question like this question where we're not replacing the ball, so the probability changes for each time you do it. Here, the probability will always be the same because they're all going to be independent events. So this will only work with independent events. And so we just have to work out all the number of ways of writing down P's and Q's. That gives us 4P's. And that would just go on for ages. And each of the probabilities are going to be the same. So we're just going to count up the number of ways. And how do we count up the number of ways? Well, we do 10 choose 4. So from 10, choose 4. And that's going to be, you write it like 10 choose 4, 10 choose 4. And then we have a formula which is n factorial over or. It doesn't look like an or factorial, and then times n minus or factorial, basically, right? So that's just where that's n or like this. So that would be 10 factorial over. You don't need to do that. Just put it into the calculator and then you get it. So that's going to be the 10 choose 4 that we put at the start, or the n choose or. This notation is there's a few different notations. There's n c or. Sometimes you can do c n or. That's n k, isn't it? They use K and or interchangeably here. So there's a few different ways that you can write it. Personally, I prefer that one. There we go. So we toss a coin 4 times. So n is equal to 4. Here, k is equal to 2. Our formula is n choose k, e to the k, q to the n minus k. This is the formula for the binomial. And okay, so what do we want? We want exactly 2 heads. So k is equal to 2. So what do we do? So, and now the probability P is equal to the probability from a coin of a head is 0.5. The probability of not a head is the tails, which is also 0.5. So now what we do is we do 4 choose 2, and then P to the k, which is 0.5, which is P to the power k, times to the power 2, and then 0.5, which is q to the power of n minus k, which is 4 minus 2, which is 2. And then when we do all that, we get 0.375. Okay, so we have another sort of question here, right? So what we have is the defect rate of a machine is like 2%. And we want to find the probability of one defect in 10 items. Now, this is how we make maths easy, right? So we have just done this example, okay? But we've done it with a different example. Maybe it's slightly new. So let's just work it out. So let's just write down this thing. And incidentally, I believe it's probably, let's just have a look here, the probability section, somewhere page 18. Probably it's there, right? So there it is there. So we do have the formula in the book, right? So we're talking about the binomial distribution. How do we know that? Because it's like, basically they're talking about, the probability of the defect is, so it's either defect or not defect, right? So that's binomial. That's just like 2 possibilities, right? And then it's like, find exactly, 1 defect from 10 items. So enough of that should be enough to say like n choose k. As I said here, I think they're using like or, p to the power of k. Doesn't matter that they're using p to the power of n minus k. So we've written down the formula. Now what do we need? We need n, k, p, q. And at this point, I would go as far as saying that the question is done. Okay, because, the reason why you're going to get a math problem wrong is because if you don't know what to do, right? But if you've done this bit, then you know it's binomial. Then you find each of these values, 10, 1. Now, 2% defect, I can't write down 2%. This is 0.02, 0.02, and this is 0.98. Okay? Now we're going to sub it in. So it's going to be 10, choose 1, and then it's going to be 0.02 to the power of 1 times 0.98 to the power of 9. So like there's something about a maths problem where it has this type of shape like this, and it's sort of like this is difficulty here, right? So essentially the hard part of a maths problem is just like what are we doing? Like what is this question? So it's really the diagnosis. Like if you know it's a binomial, this is the formula, this is the end, then you're up here. And from that point there, it's all now this may cost you time, right? But it shouldn't cost you effort. Maybe it takes a lot of effort to do this in like 1 minute and not a lot of effort to do it in 2 minutes, right? Now, you have to also bear in mind that when they structure these exam papers, they like they don't want you to be doing this at breakneck speed, right? Like there is a lot of pressure, but the main pressure that you'll have in a question is get to the point of understanding like what to do, okay? And so that's just diagnosing what kind of problem it is. Okay, this is the formula that we need for that type of problem. If that's the case, what are the n, the k, the p, and the q? Let's go back and read the question. Okay, 1 defect in 10 clearly makes that n is 10, k is 1. And then what's the probability of finding 1? So this is the probability of finding the defect is p, so this is 0.2. Now, if you made the mistake and you swapped these two, if you said q was 0.02 and this was, then you're into the 7 out of 10 territory, right? But I don't want you to really kind of care right now at the moment whether or not you're getting 7 out of 10 or 10 out of 10. I would even forget about 10 out of 10 right now. Think of it like this, right? So if you diagnose it properly, this is like 3 or 4 out of 10. To get this, to write that down basically, is when you've essentially kind of, that's like, but that's like kind of, it might even be 5 out of 10, right? This could even be 5 out of 10 here. Now, the ball rolls down the hill from there. Now, maybe it doesn't, maybe it stops there, in which case it gets a 7 out of 10 or goes to here to get to this last stretch is like kind of refinement. This is like later, right? This is like when you finish the whole course and you're like, you're in the last, whatever, 2 months or something. And that's when you start, and you've done all the exam papers. And now you go, okay, let's take a serious look at how to get those last few marks. Okay. But what you need to do is do this in sequence. Make sure that you can get to this stage, which means diagnosing every problem correctly now, or not for the stuff that you haven't done, but for the stuff that you've covered, or when you finish the section, you can look at past exam papers. Make sure you can diagnose what formula I need to use, pick the right method, and just do that for every question. Then I would go back through the exam papers and actually try to get down to the point of writing something like this without making a mistake. And then at the end, I would just like do the rest of the figuring out. Don't have to do it that way, but it's just good to give yourself, like, it's terrible that you have people sort of reaching for the 10 out of 10 and then kind of collapsing and get 0 out of 10. Like that just should not happen. You should definitely be getting 3 out of 10, 4 out of 10 very confidently, and then getting 7 out of 10 kind of confidently, and then just worrying about the higher grades like after that. And then we have some other topics that I won't talk about now. We're going to talk about mean and variance and stuff next time, I think, tomorrow. I'll just have to have a look at my at what I have planned for then. So maybe just tiny quick look at this in the last minute. So, okay, this one here, to solve this, I would have left you to do this by yourselves, but so the probability of A is 0.4, the probability of B is 0.5, and then the probability of, so there's a 0.2, there's a 0.4, no, there's a not, this is A, okay, and this is B. So there's a 0.2, there's a 0.2, and there's a 0.3. See, in total in A, there's a 0.2 and a 0.2, which gives us the 0.4. And total in B, there's a 0.2 and a 0.3, which gives us the 0.5. And in the intersection I've got, so we can see there's a 0.2, a 0.2, and a 0. That's a 0.3. So that's now that's a perfectly valid way to do this question, just with Venn diagrams. Otherwise, you can use the formula. It's weird. Like formulas are they're almost false friends. Like they can actually make the topic harder because we're like, I don't need to understand this. I just need to But when the understanding doesn't take that much and you can just get it from a picture, so this is 0.4 plus 0.5 minus 0.2 is 0.7, you see. And then the second one, the probability of B, well, this is the probability of being in the intersection divided by the probability of B. So this is equal to the probability of being in the intersection is 0.2 and the probability of B is 0.5. So that's 2/5 or 0.4. Okay, great. And the last one is a binomial. N is 5. You see the probability K is 3 or as you may like. P is 0.6. Q is 0.4. And the formula, N choose K, P to the K, Q to the N minus K. Just sub it in. Okay, so I hope that was helpful. So yeah, I'll send over the video later so you can look back at it, and I'll send you over a homework sheet as well. And then, yeah, hopefully then see you guys then tomorrow. Okay, thanks for joining me.